Your data never travels whole. Not your photo, not your message, not this video. The internet looks at your file, shrugs, and tears it into pieces. On purpose. Right now, as you watch this, thousands of tiny fragments are leaving servers across the world. They're taking different routes. Some are late, some get lost, some are copied, just in case. And somehow, miraculously, they all reassemble on your screen, in the right order, at the right time, pretending nothing chaotic just happened. That smooth progress bar you trust? It's lying politely. Because the internet is not a single road. It's a crowded, argumentative city with no central planner, no boss, no guarantee that any path will stay open for more than a moment. So engineers made a strange decision decades ago. Instead of protecting your data, they decided to sacrifice it, chop it up, scatter it, and hope enough pieces survive. It works, mostly. And the reason it works says something uncomfortable about speed, trust, and how fragile the digital world actually is. When people say the internet, it sounds singular, like a thing, like a place. It isn't. There is no master cable, no control room with a big red switch. The internet is a deal, a very old, very informal deal between machines that don't trust each other. In the late 1960s, the problem wasn't cat videos or cloud backups. It was war, specifically a very cold one. Military planners had a nightmare scenario. One bomb hits one city, and suddenly communication collapses. Phones go dead. Orders stop flowing. Silence spreads faster than panic. So researchers asked a backwards question. What if the network assumed failure was normal? What if parts of it were always broken? Traditional systems back then worked like railways. One track, one route, miss it, and you're stuck. The internet's early architects hated that idea. They wanted something messier, something that didn't care which road was taken as long as the message eventually arrived. That's where the breaking began. Instead of sending one complete message, the system would cut it into small packets. Each packet gets a label, where it came from, where it's going, what order it belongs in. Then it's released into the network like a note in a bottle, or more accurately, like thousands of notes in thousands of bottles, all thrown into different rivers at once. No packet knows about the others. They don't travel together. They don't wait. They don't even take the same path. Routers along the way make fast, shallow decisions. Is this path busy? Drop it there. Is that link down? Send it somewhere else. They don't ask permission. They don't check the full picture. They just move packets along and hope the math works out. And usually, it does. If one packet disappears, the system doesn't panic. Your computer notices the gap and quietly asks for that piece again. You never see the request. You just see the video keep playing. The message keeps typing. The illusion holds. This wasn't designed for elegance. It was designed for survival. The irony is that this fragile-sounding approach scaled better than anything before it. By assuming chaos, the internet became calm. By giving up control, it gained reach. And by breaking your data into pieces, it learned how to go everywhere at once. Of course, there's a cost to that decision. And it doesn't show up until the network gets crowded, hostile, or very, very fast. Because once you break data into pieces, you inherit a new problem. Not delivery, recovery. Imagine mailing a book by ripping out every page, numbering them, and sending each page through a different postal service. Some pages arrive early, some arrive late, some arrive twice. Some never arrive at all. And yet the reader expects the book to read smoothly without missing a sentence. That's what your device is doing. Constantly, at absurd speed. Every second, your computer is juggling thousands of packets. It's tracking what arrived, what didn't, what's out of order, what needs to be resent. This bookkeeping is invisible, but it's not free. It costs time. It costs memory. It costs patience. This is where the uncomfortable math appears. The faster the network gets, the more brutal packet loss becomes. Lose one packet out of a million? Fine. Lose one out of 1,000 at high speed? Suddenly, the system slows itself down. Not because the connection is weak, but because the protocol is cautious. TCP, the workhorse of the internet, was designed to assume congestion is its own fault. If packets go missing, TCP doesn't blame the router or the cable or the universe. It blames itself. It slows down, dramatically. Then it creeps forward again, carefully, like someone apologizing for a mistake they didn't make. This behavior made sense when networks were fragile and expensive. It's less charming when you're on fiber optics moving gigabits per second. One dropped packet can force a cascade of hesitation, a momentary stutter that feels like lag, even when the hardware is flawless. To hide this, modern systems cheat. They buffer aggressively. They predict what you'll need next. Streaming apps download seconds ahead. Browsers open multiple connections at once. Data is duplicated, guessed, and sometimes thrown away just to preserve the feeling of smoothness. And then there's security. Because packets travel independently, They can be intercepted independently. Your data is encrypted not because the internet is dangerous, but because it's nosy by design. Every router gets a peek at where a packet is going. They're not supposed to read the contents, but the fact that they could is the entire reason encryption became non-negotiable. So the system that gives us resilience also creates exposure. The thing that makes the internet fast makes it fragile. And the hacks, slowdowns, and mysterious outages you hear about, they're not glitches. They're symptoms of a system constantly negotiating with itself, one packet at a time. This system isn't just reacting to chaos anymore. It's creating it. At a certain scale, breaking data into packets stops being a safety feature and starts becoming a weapon. Not intentionally, structurally, because if you can overwhelm the system with packets, you don't have to break anything. You just have to make it hesitate. This is how modern outages happen. Not with dramatic explosions, but with floods. Too many packets, too many tiny requests asking politely for attention. Routers don't crash, they drown. Buffers fill. Queues stretch. Decisions that used to take microseconds start taking milliseconds, then seconds. And suddenly, the illusion cracks. A video freezes, even though your internet speed test says everything is excellent. A website loads halfway and gives up. A payment fails, not because the bank is down, but because one packet in 1,000 didn't come back in time. Here's the quiet irony. The internet was built to survive nuclear war. It struggles with popularity. At global scale, packet routing becomes a probability game. Every shortcut adds risk. Every optimization assumes patterns that might not hold tomorrow. Engineers constantly tune systems to guess what normal looks like, knowing full well that normal changes hourly. So they add layers. CDNs copy your data closer to you. Load balancers split traffic like casino dealers. Protocols like Quick try to sidestep TCP's old habits. Entire companies exist just to shave milliseconds off packet recovery, not because users demand perfection, but because the system punishes hesitation mercilessly. And still, the internet keeps lying calmly. When it works, it feels centralized. When it fails, it reveals what it really is. Millions of independent decisions made blindly, at speed, with partial information. This is also where trust quietly erodes, because packets don't know who sent them. Routers don't care why they exist. The network delivers data, not meaning. Spam, misinformation, attacks, live next to your family photos, indistinguishable at the packet level. Same rules, same paths, same fragility. The system doesn't judge, it forwards. That neutrality is powerful. It's also dangerous. Once you see this, the internet stops feeling like infrastructure and starts feeling like weather. Predictable in patterns, uncontrollable in detail, always moving, always one surge away from disruption. And the scariest part isn't that it breaks your data into pieces. It's that this is the only reason it works at all. The internet doesn't protect your data by keeping it whole. It protects it by assuming pieces will be lost, delayed, duplicated, or misunderstood, and designing everything around that expectation. That choice gave us scale, speed, global reach. It also locked us into a world where reliability is statistical, not guaranteed, where smooth experiences are carefully staged performances hiding constant recovery underneath. Every app promising instant, real-time, or seamless is negotiating with this reality, not defeating it, just managing it well enough that you don't notice. And the moment you do notice, the buffering wheel, the failed upload, the half-loaded page, you're seeing the system tell the truth for half a second. As networks get faster, denser, and more automated, this trade-off doesn't disappear. It sharpens. More pieces, more paths, more guesses, more room for quiet failure. The internet won't suddenly become stable, orderly, or whole. That was never the deal. The real question is this: if the digital world only works by breaking things apart, how much complexity can we keep stacking on top before the cracks stop being invisible? And when that happens, will we recognize it as a bug, or as the system finally behaving exactly as designed? Done watching. If you like this video, hit subscribe for more cool stuff.